classical mechanics as a special case of quantum mechanics. As you know that both are different fields. Classical mechanics is used for macroscopic objects or for large-scale phenomena. And the principles of quantum mechanics, these are used for atomic and subatomic levels, such as electrons, protons, neutrons, atoms, molecules, etc. This is known to you. But here the point of discussion in today's lecture is that the field of classical mechanics that can be considered as a special case of quantum mechanics. Means the field of quantum mechanics encompasses both the quantum mechanical effects as well as the effects in the field of large-scale phenomena or the dynamics of large-scale structures. Means everything can be captured by using the principles of quantum mechanics. Here I have noted down few points such as the correspondence principle of Niels Bohr, wave function and probability densities, Heisenberg's uncertainty principle, then comes Richard Feynman's path integral formulation, then Ehrenfest theorem is there, and quantum decoherence. If you analyze all these, I have noted down only 6 points. Okay, there are much more. There are more points than this number 6. Anyway, if you analyze all these points one by one, then in each case you will find that classical mechanics is a special case of quantum mechanics. You just focus on the second point, wave function and probability densities. You know that in the field of quantum mechanics, the state of a system is defined or described by the wave function. Okay, means if the wave function of a quantum system is known, that means each and everything is known about the system. By using the wave function, you can get the desired results. Desired calculations can be made using the wave function alone. Okay, so the state of a system is known, that means everything about the system is known. And you know that square of the amplitude of the wave function, that gives you the position of the system. Okay, and if you apply the same thing for large scale structures or for macroscopic objects, then what happens, the amplitude, okay, square of the amplitude of the wave function becomes highly localized. That means if it becomes highly localized, that means you are getting in that case a definite position and definite momentum. That means you are getting the results of classical mechanics. According to classical mechanics, you know that the position, momentum, etc. this can be calculated with exact precision. But in case of quantum mechanics, you know that no, this cannot be calculated with exact accuracy, okay, or exact precision. I should rather say exact precision, but probabilities can be calculated. Okay, but in case of classical mechanics, these are exact. So if you apply these wave functions for the field of for the problems of classical mechanics, then you will get that the square of the amplitude of the wave function becomes highly localized. Okay, so that means you are getting a definite position and momentum. So I have analyzed here. I have analyzed only the second point. Similarly, if you consider the first point, the correspondence principle of Niels Bohr, then there you will get that the predictions of quantum mechanics and predictions of classical mechanics match to each other. When they are matching, when you are dealing with high energy states or large quantum numbers. If for the given system quantum number is large, that means it is having high energy state. It is existing at a condition of high energy state. So in such cases, predictions of quantum mechanics will lead to the predictions of classical mechanics. That means the correspondence principle of Niels Bohr bridges quantum mechanics and classical mechanics. Okay. So similarly, if you proceed to point number 3, 4, 5 and 6, everywhere you will find the same thing. Everywhere you will find the same thing. That means the results of quantum mechanics and results of classical mechanics are matching with each other. Okay, means everywhere you will find that classical mechanics is nothing but a special case of quantum mechanics. Whenever you are dealing with macroscopic objects or whenever you are dealing with large scale phenomena, in those cases quantum effects become negligibly small. So there is no need to use the principles of quantum mechanics for the purpose of calculation. The theory developed by Newton and others, you know that the theory of classical mechanics, that was mainly developed by Newton, and of course there are contributions of other physicists also. Okay, so and that is popularly known as Newtonian mechanics. So the principles of Newtonian mechanics or the principles of classical mechanics can easily be used for large objects or massive objects or macroscopic objects. Okay. Anyway, so this was all about today's topic, classical mechanics as a special case of quantum mechanics. Okay. Okay, so this is the end of this video. Thank you for watching this video.